today we're going to be talking about work, energy, and power. And this will start our next unit, and uh, we'll spend about 2 or 3 lectures on work and energy, and then we'll spend a couple lectures on momentum. So, what is energy? Energy is like money. It comes in lots of different forms, and you either have that form of it or you don't. So, just like money has pennies and quarters and even different types of money, depending on what country you're in, or whether it's credit on a plastic credit card or a debit card or a savings, all of these different types of money you may have some or none, and you can exchange one for the other, right? You can give somebody 4 quarters and get a dollar bill from it. So energy is very much like that. Now, the other thing about energy is it's not a vector. It doesn't have anything to do with direction. You either have this type of energy in the system or you don't. So there are different types of energy. There's mechanical energy, which is what we're going to be focusing on this time, which comes in a stored or potential energy or energy due to motion, kinetic energy, or elastic potential energy. There's also heat energy, thermal energy, chemical energy stored in the bonds of your of food that you liberate when you eat, or chemical energy in a chemical reaction. And there's electromagnetic energy, like energy carried by light through space. So we, once again, are going to be concentrating on mechanical energy. So in order to give something mechanical energy, either potential energy or kinetic energy, energy due to motion, you have to do work on the system. So think about throwing a ball. What are you doing? Well, when you throw the ball and the ball leaves your hand, it started with no kinetic energy. And by the simple motion of you applying a force to it through a distance and then letting go of it, you gave it kinetic energy. But here's the kicker. That kinetic energy did not come from anywhere. It came from some other place. You turned some type of energy into a new type of energy. You did work on that ball. And by definition, work is the transfer of energy into or out of a system. But remember, it doesn't just come from nowhere. When you throw that ball, you are taking the stored chemical energy that was liberated and stored in your muscle cells, and you are turning that into kinetic energy that the ball has when you let go of it. So it didn't come from somewhere. You gave it kinetic energy, but it had to come from some place, from some stored, type of chemical energy in your body. You can have this is called doing work on the ball. And if you do positive work, you're going to cause it to gain some type of energy, usually kinetic energy. And if you do negative work on it, you can cause it to lose a type of energy. So let's talk about negative work. So imagine that you have a ball and you push the ball and you let go of it so it has some speed and it just rolls along the table. Well, eventually it will slow down to a stop, right? So it has now lost kinetic energy. And why is that? Because while it was moving, there was a friction force acting on it in the opposite direction. And that friction force did work over that distance, right? So the work done by the friction force is in the opposite direction, but it's moving in a positive direction. So really work is the multiplication of a force times a displacement, the multiplication by 2 vectors, but you're ending up with something that's not a vector. It's called a dot product, and we'll talk about that a little later. But what's really happened is that you've transferred that kinetic energy that the ball had into heat energy. Because when friction acts on something, that's what friction is doing. It is turning mechanical energy into heat energy. Imagine lifting up a box. So if you started, if the box had been on the floor, right, and now you lift it up, you're not really giving it energy of motion, because once it's lifted up to this height, it's not moving. But you're giving it some kind of energy, because if you let go of it, right, it will fall. And that is potential energy. So Maybe you do work lifting something and you give it potential or stored energy due to its height or its change in height above the floor. So we're going to be talking about these different types of energies. But before we do that, let's talk a little bit more about work. Work is, by definition, a scalar quantity, has no relation to direction, but it is calculated by multiplying a force vector by a displacement vector. And that means that in order to do the maximum amount of work, they have to be parallel to each other. So when you're throwing this ball, so let's imagine that you're throwing a ball, okay? And you started here, okay? And then you threw it this way. So you applied a force to the right, and it moved to the right. And that gave it some kinetic energy when it came to a stop. So the force that you applied to it is a positive number, and the displacement is a positive number simply because they're in the same direction. Now, you can do work dragging something at an angle, but that rope that you're using to drive it at an angle, that tension is not doing all the work, only the horizontal component. So it's really important for you to know that the force and the displacement vector have to be parallel to each other. The units are going to be newtons times meters or joules. So whenever we calculate work, we want our force to be in newtons, we want our displacement to be in meters, and when we multiply a newton times a meter, we get a joule. So let's just also look at what a newton meter is in addition to a joule, okay? A newton is a kilogram times a meter per second squared, and then you multiply it by a meter. So really, it's also a kilogram meter squared all over a second squared. So a newton meter or a kilogram meter squared over second squared, they are both called a joule. Those are the equivalencies for a joule. So let's talk about now what happens if we pull a box with a rope. So remember that when we do this, and let me just make this a little smaller so we can see the whole thing. When we pull it at an angle, right, it has an X component and it has a Y component. We're lifting up on the box and we're pulling it to the right. The force that's actually causing the acceleration or the change in motion is Fx. So Fx is the force that you're pulling with in the rope times cosine theta. So the work is really Fx times the change in position. Right? And I'm just putting my little vector arrows here to remind you that these are vectors. And that is really F times cosine of the angle that you're holding the rope at times delta X. And if we rearrange it, a lot of times we'll see the formula for work is F delta X or R times cosine of theta, where theta is the angle between the force and the displacement vector. So here's your force vector, and here's your displacement vector. Right? You move from here to here, and that angle is the angle between them, which in this case is the angle that the rope is held at. So in order for the maximum amount of work to occur, right, maximum work would occur if theta is 0 degrees, right? That means that there's no angle between them where they're completely entirely parallel. But there will be 0 work if theta is 90 degrees, because think about what that means. It means that the force is acting completely up and the displacement is to the right. So that would be 90 degrees, and there would be no X component causing that motion. So an example of that would be like if I said, how much work is done by the normal force on this box? Well, the normal force is here, right? And the angle between the normal force and delta x would be 90. So if I put cosine of 90 in there, that would be 0, and there would be no work. The normal force does no work moving this box, and that makes sense. It's not contributing to it. But you are applying Fx to it, and that's what's doing the work to it. And once again, the units are still newtons times meters. So sometimes you'll see the formula written with cosine theta, and that's to take into account that sometimes the force is at an angle to the displacement. So let's do a couple of examples. A man pushes a 50-kilogram lawnmower using a 100 Newton force applied to its handle that makes a 30-degree angle. So we're going to draw our box. So once again, our diagrams don't go away. We are, to think about it, you know, you've got a handle here. So there's like a force going down at an angle that makes a 30-degree angle with the box. So if I were to actually talk about what's going on there, I'm pushing it forward and I'm pushing down on it, right? So the forces that are really causing the motion here are Fx, and I'm pulling down on it with Fy, and it has weight, and it has a normal force. So in the y direction, Fn will be equal to the y component plus the weight, because all the forces are adding up to 0. But in the x direction, Fx is causing it to accelerate. Okay? So what does this have to do with the problem? Well, I'm just reminding you that this is how we're always going to look at these problems. We're going to draw a vector diagram. We're going to look at what's going on in the y direction, and we're going to look at what's going on in the x direction before we actually solve the problem. What it wants to know is how much work does he do pushing the mower 10 meters. So work is equal to Fx times cosine of theta. And in this case, the angle is 30 degrees. So this is going to be, he pushes with 100 newtons for 10 meters. And the angle between the 100 newtons and the 10 meters is 30 degrees. So the work is going to be equal to 100 times 10, which is 1,000, times cosine of 30.5 will be 500 Newton meters, or 500 joules. So what kind of energy did you give it? Well, you gave it kinetic energy. The work that you did on this was taking that stored chemical energy in your muscle cells and pushing that box and giving it speed. So now it has kinetic energy. So you have a transfer of energy in, and that is why it is positive. It is not positive because it's moving to the right, because work is a scalar quantity. Let's talk about lifting something. So let's say you have a girl and you lift her 4 meters. So I'm just going to draw what's happening, kind of sketch it out. You've got a girl and you're going to lift her 4 meters. So imagine that if you're lifting this girl, right, at a constant speed, we're just going to assume at the bare minimum a constant speed. Well, she has weight, and you are lifting with an applied force, and that applied force has to be equal to the weight, bare minimum. So, and you are going to lift it a displacement of 4 meters. So in the y direction, just to remind you that all of those forces add up to 0 because it's traveling at a constant speed with no acceleration at the bare minimum. And that means that Fa that you're applying has to be equal to the weight in magnitude, right? And so the weight of this girl is just mg, or 60 kilograms times 9.8 meters per second squared, which is 588 newtons. And So that's our force that we're applying. And then, of course, delta X is 4 meters. Now, these are both in the same direction. So the angle between them is 0. So cosine of 0 is 1. We don't have to worry about that cosine factor. We can just use work equals F times X, which is 588 newtons times 4 meters. So 588 is 2.35 e to the 3. So 2.35 kilojoules. Now, when you lift it, you're going to be giving it potential energy, right? You're going to be giving it potential energy. What if she falls down 4 meters? How does that change? Well, actually, let's just add another page here. So now she's going to fall down 4 meters. The force that's going to cause her to fall down is Fg. So in the y direction, she's accelerating, right? She's moving and getting faster. Fg equals mg. Now notice that Fg is a negative number, right? And her displacement is a negative number. So the force that's causing her to fall is negative mg, and the displacement that she's falling is negative 4 meters, right? She's falling 4 meters. So it's going to be negative 588 newtons times negative 4 meters is still going to be 2.35 e to the 3 joules. It's going to be positive, but she doesn't gain potential energy in this example. She's gaining kinetic energy. So the potential energy she had at the top of 4 meters is being converted into kinetic energy, assuming there's no loss due to friction. All right. So now let's talk a little bit more about that transfer of energy and a word that you're familiar with, power. So imagine that you're running up the stairs versus walking up the stairs, right? Obviously, running up the stairs is going to make you feel more tired. But if you think about what you're doing in both of those scenarios, right, you are lifting your weight the same height, right? In both scenarios, your delta X is the height of the stairs. So you may be a 588 Newton person. You may be running up the stairs or walking up the stairs, but the end result is the same. You have given yourself the same amount of potential energy, 2.35. So let's say this was your 4 meters and you were 588 newtons. So whether you walk up the stairs or run up the stairs, you're going to do 588 newtons times 4 meters in both situations. You're going to be tired, though, because the rate that you transferred your stored chemical energy into potential energy was much faster when you ran up the stairs. Power is the amount of energy that you transfer from one type to another type over time. It's the rate that you transfer energy to another. And it's going to be measured in joules per second or watts. So in this case, let's say that we lifted that person, whether we ran or not, we did the same amount of work, right? the work is the same. It's 588 times 4 meters, 2.35 e to the 3 joules. But if we did it in 1 second, we would have converted all of that 2.35 e to the 3 joules into potential energy in 1 second. Versus if we did it over 10 seconds, the power would be 1/10 as much, right? We didn't have to convert as fast. We did it over 10 seconds, 10 times longer in order to get that same transfer of energy. So when you pick something up, you're always going to do the same work against the gravity, but the power is different because power is inversely related to the time over which that energy change occurs. So the more time it takes, the less power dissipated. So let's just do an example again with some numbers. So we're lifting a 588 Newton man up the stairs, and it's 2 meters high in this case. So the work done in both instances, whether we walk up the stairs or run up the stairs, is always going to be 588 newtons times 2 meters, which is going to be 1.18 e to the 3 joules. In any case, whether they run, jump, whatever, as long as it's the same weight, the same distance. So the power would be that amount of work divided by 30 seconds, which would be 39.2 joules per second. So you had to convert 39.2 joules of chemical stored energy into potential energy every second to do that job. If we cut the time in half, because it is an inverse relationship, then the power would be exactly the inverse of that, which would be 2 times as much. So you would have to do 2 times as much work. Well, the same amount of work, but in half the time, means that the power rating would be 78.4 joules per second. So if you have to do it in a shorter amount of time, you're going to have to convert more joules every second to get that same amount of work done.